So first we're going to start with correlation. Correlation and linear regression have a lot in common. So we're going to start with this and kind of move forward step by step. Please stop me if you have any questions. Like I said, this is very important and it's good to understand pretty thoroughly. Okay, so we're going to talk more about what correlation is and what it means. So that'll go over that in the next slide. We'll start here actually. So correlation coefficient measures the relationship between two continuous variables. So the example that I have given today, I'm going to go in and not show that yet. So the example data I'm using today. All right, what is going on? There we go. Is something that I created. I actually called it linear model data. One of the better data sets for this that is available publicly and is pretty widely used and also simple is the census data. Anybody can download it. So for our predictor variables, I will be using census data. Again, all the data sources are in the statistics in R folder. So if you want to know more about it, please go in. But today we'll be looking at educational attainment, the percent that is married, percent below the poverty level, and percent, and this is health insurance, so uninsured in 2014. I'm using 2014. There's a lot more recent data, but I thought it would be interesting to look at those census data. These will be our explanatory variables. And we will be looking at the heart disease mortality rate will be one thing that we're looking at here as as our response variable. And we'll talk more about that. And then we'll also be looking at life expectancy. The latest that they had was 2014, so I went with this. I always try to keep the FIPS codes in here because if you ever want to use this data, you need those to merge in if you wanted to merge in other variables. So as you can see, this is county level data. So we're going to be using this for the entire class today, and we're going to be using that as examples. So correlation coefficients, they always range from -1 to 1. We'll talk in a minute about what that means in detail, but in general, the values closer to 0 means that they have a weaker relationship. Values closer to -1 or 1 have stronger relationships. You can think of this as the higher the absolute value of our correlation coefficient, the stronger the relationship is in general. So that would be a rule to think of this as.
And so, 0 is no relationship, yes?
0 relationship, if you put something random for both of those variables, it would likely be close to 0. So if you had a random number generator and did variable 1 and variable 2, in general, it would probably be right around 0 because there wouldn't be a relationship. So if you see that, there is no association or relationship between those two variables. We're going to talk more about the definition of that because it is important in this concept. And we're going to talk about correlation does not equal causation. Just because two things are associated with one another doesn't mean one causes the other. We'll get more into that with some really shocking examples. But in general, the higher the absolute value, the stronger the relationship. And we're going to talk about what negative and positive mean and what they would look like in between in just a minute. So more about this. Correlation coefficients, the direction matters. So whether it's negative or positive, it means two different things. I have visuals on the next slide. So a negative correlation coefficient means that there's a negative relationship. That means as one variable is rising, the other is falling on average. So a positive correlation indicates a positive relationship, which means that as one variable is rising, the other variable is also rising. So that is the very basic idea of this, and we're going to go over how it's calculated and more about this. So on this basic information, without getting into the formula, are there any questions?
So high level, the negative correlation, you say it's a negative relationship, but I think about it as an inverse relationship.
Yes. And I'm going to show actual figures that give you a great idea of what that looks like in a second.
Yeah.
But an inverse relationship, there's a lot of different names for it. But negative might be the easiest way to think about it because it's actually a negative correlation coefficient. But you can use indirect or direct relationship, inverse versus direct relationship. There's a lot of different names. That's somewhat frustrating about statistics. There's usually 5 different names for everything. I've been at work and we're arguing about something, and then we actually realize we're both talking about the same thing, but we're using different language for it. So that happens.
Yeah, one other thing is that in the book they specifically called this Pearson's correlation. Yes.
Yes. So there's 2 different types of correlation. The Pearson's correlation is what I'm going to be going over today. That is relevant. I should have put it in here. There is rank correlation as well. I didn't put it in these slides, but I can give you a high level overview a little bit later. It was just too much material, and it tends to be pretty simple and very similar to Pearson's correlation. But it's something we call a rank correlation. So I'll quickly go into that, but I'm not going to go into the details. So this would be Pearson's correlation. And I will, again, put just like usual, put these slides, the updated version, and online.
The rank coefficient is the Spearman's rho that they're
talking
about, yeah?
Yes. And that is an important distinction, and we'll talk more about that once we get into what correlation actually means.
But not this week.
Yeah, I probably won't go over it in detail because it's so similar, and I can probably give you in like a synopsis of the differences. And then if you want to know more, look it up yourself. And after you do regular correlation, it will be pretty easy for you to understand documentation.
Yeah.
So correlation strength. So when we look at this, as Michael said, anything from 0 to 0.3 or from 0 to negative 0.3 tends to be weak or no relationship at all. So if you see this, it's not a substantial relationship. It's probably not meaningful in practice. So I'm going to go over a little bit about the actual practical implications versus whether it's significant in a little bit. But 0 to 0.3 and 0 to negative 0.3 tend to be a weak or no relationship. In general, this is a rule of thumb, but other people might define this differently. This is the breakdown that I see most often. Looks like there's a question. A glossary of terms. Yes, we should also have cleaner data, and we should also have a lot of different things. We should have data dictionaries, but it's just, in general, when you work for any company, you're going to see that it's not always done in a perfect way. And it's just the way it tends to be. No matter what company you work for, there's going to be downsides, and usually documentation, data dictionaries, and that tend to be a little on the lacking side, but it's generally something that most companies are working on as well. So so if you're looking at the correlation coefficient, 0.3 to 0.7 or negative 0.3 to negative 0.7 tends to be a moderate relationship. So somewhere in the middle. If you see towards the end of this scale, so I've done, and I can't tell you any more details about this, but I put a model into production at one point. My model came out, and the correlation between my predicted and my actual values was close to 0.7. And that was looked at as a pretty good thing, given, and it depends on the domain and how predictable things are, but that was looked at as something that was a positive. So that was enough for them, as an example. And then if you have 0.7 to 1.0 or negative 0.7 up to negative 1.0, that tends to be a strong relationship. Since we're talking about this, I'll go over the formula for correlation after these two slides. So this gives you an idea of what I mean in practice that correlation looks like. Okay, so what I'm showing here are positive correlations, meaning there is a direct relationship or a positive relationship. Now you can probably understand a little better what I mean. So I used a lot of materials from different websites, and I put all of the links down here. So if you're interested in learning more, they seem to be pretty good on the actual teaching section. And I also put a link slide at the end of this this PowerPoint for things that I thought were pretty good and that might not have been on the reading. So a correlation equals 0. This means that there's no relationship whatsoever. It's going to look something like this. So we do not see a trend here. The trend would be is horizontal. That means that there's no or likely no relationship between both variables. And as far as a relationship, that means that, say you're over here in 0.6. As I said, that means as one is rising, the other one is rising. Another way to think of this, in previous classes, we've gone over variance. So the standard deviation is the square root of the variance. And mathematically, this means that they vary, or their variances are similar, and the variances go in a similar direction. So the actual math of it, that's what it means as well. So you can try to think of it in different ways. But as you see here, we have a moderate relationship here. So you see, and actually these are switched. I apologize. This would be a moderate relationship. And the reason I knew that is because this one is more spread out, and there is less of a correlation, meaning that these lines are more randomly distributed. There is a wider range here, although we do still see if they were going to put a line, which we'll go over today with linear regression, put a line through this, it's still rising. And this is something that we would call a moderate relationship. So there's definitely something here, but it's not to the point of strong. Whereas this correlation here, you can see that they're more tightly packed together. They're following this upward trend, or much closer than these over here. And that is something that we would call a strong correlation. So if you see 0.8 in work that you do, that's a pretty good indication that there is definitely a relationship. And not only is there a relationship, it would be meaningful in practice. So it gives you some good information. And then the last one that I'll go over is the perfect relationship. So if there was a 1.0 correlation, you would see that it would follow a straight line here. And that is what we would see. All of these are positive correlations. Now I'm going to go over the negative correlation. So this will give you a good idea of what that means. This is the same picture that you saw for equals 0 in the slide that you just saw. But you can see here, so as one variable is rising, the other is falling. So if you are, your x-axis is rising here, your y-axis is falling. So we're going to see some practical examples later, but if you were going to draw a straight line through this, you would see that it is going down, and that's the direction that you're going to see with the negative correlation, is down. But again, you can see that they're not very tightly packed together, but they are following a very obvious trend. So this would again be a moderate relationship, just in the negative direction. So here we're seeing correlation equals -8. We're seeing again that this is more tightly packed together. If you drew a line through it, everything, those points would be closer to that line. And so this would be a moderate negative or strong regular negative relationship. And again, if we're looking at -1, we're seeing that downward, those downward points, and then it is in a straight line. So this is a perfect relationship. They are, when you look at them, there is a straight or a straight relationship between those two. So it would be a straight line. So this is what I would mean by a negative correlation. Before I ask for questions, I'm going to go over one more thing. So going forward, at the beginning of these classes, I tried to not use formulas, but I think that was in an effort to, as you did this, to get your feet wet and not overwhelm you with symbols and formulas that might be somewhat confusing. However, if you ever read a statistics book, they're all going to have formulas in them. So I'm going to start on these a little more complex. Now that we have an idea of statistics, I'm going to start using those formulas. So when you go into a statistics book, you're not going to be overwhelmed by it. So here we have R, X, and Y. So the symbol for correlation coefficient is R in almost every case. So R is equivalent to the correlation coefficient. These subscripts here are saying that it's the relationship between X and Y variables. The next one that we're seeing here is Xi, the values of the X variables in a sample. So when you're going through and you see down here, when you see Xi, you can think of that as symbolizing X1, X2, X3, X4, all the way up to the end of our sample. Say we have 30 values in our sample. It would be X1, X2, X3, all the way with that relationship to X30. So as you see down here, this always means sum. So the X1 symbolizes that we're going to go through each of the points in our data set one by one. Like I said, this is the same as X1, X2, X3, referring to the different rows in our data set. The mean of the values is always going to be X bar. So when we see that down there, we would see that we have all of our different points, 1, 2, 3, 4, so on and so forth, and we would subtract the mean from that. We see Y here, and that has the same meaning. So going through Y1, Y2, Y3, Y4, and subtracting the mean of those groups. And then we will find the sum of all of these different, we would do the math here and then sum all of the values. And you're seeing down here that we are putting this is our numerator, and our denominator is the same or very similar, except we're squaring those values and finding the sum of each individually. And then we are finding the square root. So why would they do a square and then find the square root of that? It sounds counterintuitive. There's a reason for this mathematically. So I'm going to go over more of this later. But when we have this correlation, say we drew a line through this, some points are going to be below the prediction line, some are going to be above the prediction line. And if we didn't find the square of them, we would basically be adding positives and negatives in our data. And we want to look at the relationship or the absolute relationship. So we want to look, I apologize. We want to look at how much of a trend there is, regardless of if they're above or below what is predicted. So when you see that, it is almost always in the realm of statistics a way to use the information without mixing up positive and negative values.